I'm just trying to give this a fancy name because it's still about carbon capture and sequestration to, continue the mitigation fast enough to reduce or at least keep a chance of sticking to the global warming targets. And it's a feature article that just appeared, so it's new, and it's a feature article means it talks to people, tends to be more about what's happening on the ground as opposed to, we've discussed carbon capture in so many ways, technical aspects and some socio-economic aspects and so on and so forth. So let's read one more. It just adds to the spectrum of articles we need to track anyways. So here is a facility in Iceland run by carbon capture companies Climeworks and CarbFix that pull carbon dioxide from the air and store it below ground. It's always a matter of the scale of things. We need gigaton scale drawdown, and nobody is at that scale yet. But so many people are working on this full time because the economic incentives are quite large. So this will go on. 3 ways to cool the planet by sucking up carbon. With the world set to blow past its temperature targets, efforts are growing to pull carbon dioxide out of the atmosphere. Okay, sometimes in the next several months, a team of US scientists plans to pour a solution of antacid into the waves off the coast of Massachusetts. Using boats, buoys, and autonomous gliders, the scientists will track changes in water chemistry that should allow this tiny patch of the Atlantic Ocean to absorb more carbon dioxide from the sky than it would normally do. So that's the additionality that we are always looking for. The US $10 million experiment dubbed Loch Ness, the Loch Ness monster, aims to test one prominent strategy to reverse global warming by removing CO2 from the atmosphere. Here it's LOC hyphen Ness, NESS, not Loch Ness. Doing so will be neither cheap nor easy. But with the world looking likely to blow past the temperature targets laid out in the 2015 Paris Climate Agreement, a growing number of scientists and policy specialists say that carbon removal will be necessary later this century if humanity is to achieve its long-term climate goals. Obviously, the issues are if you become very successful at drawing down carbon, then maybe people think it's okay to burn fossil fuels because anyway we are taking CO2 out of the air, but there are many other issues associated with burning fossil fuels. But anyway, governments, utility companies, and hundreds of startup organizations around the globe are now investigating billions of dollars in carbon removal strategies that take 3 broad approaches: sucking carbon directly from the air, direct air capture DAC, altering the oceans to absorb more carbon dioxide than normal, often it's called ocean CDR, ocean carbon dioxide removal, and enhancing carbon removal on land, often also includes nature-based solutions where you enhance natural sinks and reduce natural sources of carbon. In the United States, for example, companies are planning to build several large-scale direct capture facilities that scrub CO2 out of thin air, and in Europe, power companies are developing a strategy that captures carbon emissions from the bioenergy plants that burn wood chips, straw, and other plant-based materials. The captured CO2 will then be pumped into the ground beneath the North Sea. Many companies are already selling voluntary carbon removal credits to organizations such as Microsoft and Google to help them meet their climate commitments. By some estimates, the world might need to remove more than 6 billion tons of CO2 from the atmosphere each year by mid-century to meet its long-term climate goals. So that's under catching carbon, we'll look at in a minute. If such approaches succeed, these technologies could help many nations and corporations to meet their climate commitments and help the world to halt global warming. Halt global warming? Well, yes. But the carbon removal industry faces stiff headwinds owing in part to a lack of international standards for such technologies and formal commitments by the governments. Another major hurdle is a political sea change under United States President Donald Trump's. The US had been the largest government backer of research and development for carbon removal technologies, but Trump is now scaling back climate and clean energy investments. Most importantly, say researchers, there are also scientific questions about whether the budding market for carbon removal and the technologies can live up to the hype. This is where academic research projects such as Loch Ness come into play as a way to test carbon removal strategies in real-world settings. Although the basic science behind this type of ocean experiment is sound, researchers aren't sure how it will work in practice. The details matter, says Adam Subhas, a geochemist at the Woodsole Oceanographic Institution in Massachusetts, who is heading up the 4-year Loch Ness project. There is all sorts of activity in the private sector, Subhas says, and it's really critical that the science keeps pace. So if only the capitalists take it over, as they are trying to do with solar radiation management, spraying stuff in the atmosphere and so on, then the science has to be there to say whether that will have unintended consequences, whether it really works, or government money is being taken up, and so on and so forth. Pulling carbon from the air, then, the cheapest way to draw carbon out of the atmosphere is to grow more forests, but trees are not necessarily a permanent solution because they might be cut down or burned in fires, which are a growing threat. Wildfires are increasing across the board. Many scientists and industrialists therefore focus on more permanent and more expensive solutions. The simplest method is industrial scale direct air capture, but it's also the most expensive, costing in the region of $600 to $1,000 per ton of CO2, which is roughly 10 times higher than the price of carbon credits on the European Union emissions trading system. So the cost per ton is always a key measure of how successful you are. What, of course, scaling it up to many many thousand tons will matter. What will become the world's largest direct air capture facility is expected to What will become the world's largest direct air capture facility is expected to start operations later this year in West Texas as a joint operation between two companies, Houston-based Occidental Petroleum and Carbon Engineering in Squamish, Canada. Oil companies have a big interest in carbon capture because then they can say we'll keep selling oil and using fossil fuels because we are capturing carbon, right? The consortium plans to bury 500,000 tons of CO2 captured each year underground. The group is also developing a second facility as part of a direct air capture hub that received $600 million grant commitment from the US Department of Energy under former President Joe Biden. Another $600 million commitment from DOE went to a second air capture hub in Louisiana, which features a pair of facilities that will use technology from Heirloom Carbon Technologies, a firm in Brisbane, California, and a Swiss company called Climeworks based in Zurich that operates what is currently the world's largest direct air capture facility in Iceland. Okay, so catching carbon. The International Energy Agency projects that carbon capture could play an important role in limiting global warming to 1.5 degrees C, but to do that, the world would need to vastly increase the amount of carbon that is removed from the atmosphere and then used or stored. So the projections are millions of tons of CO2 removed from 2010 to 2020, and then it has flattened a little, COVID, etc. But projected, if you look at going from here into the future, the IEA's roadmap to reach net zero emissions by 2050, carbon pollution from the combustion of fossil fuels and biomass would drop by 98%, and carbon capture would rapidly rise. So these are projections, which means you are going to assume technology will be or should be available to do this if we want to meet the 1.5 degrees C warming threshold by 2100 with some 67% probability. So is this going to happen? Well, let's see. Both the DOE hubs will pump carbon they extract from the atmosphere underground with funding from an infrastructure law passed by Congress in 2021. The DOE had planned to invest another $2.3 billion in the air capture project, but Since Trump took office, the DOE has frozen the funding for that program, including money committed to the plants in Texas and Louisiana. It remains unclear whether and when the agency will fulfill even its existing grant commitments, which many specialists fear will threaten the viability of both the hubs. We don't actually know whether the Trump administration will honor these contracts, even though they are legally binding, says a person who worked in carbon removal at the DOE before being fired alongside roughly 2,000 other probationary employees in February. It puts a lot of these projects in a really risky place, says the former DOE employee who declined to be named because of concerns over potential retribution. Well, many of these probationary employees who were fired from government agencies have been put back into employment because of a court order, I think. Others fear that the Trump administration will take further steps that slow advances in this area, such as freezing funding that was set aside for the purchase of carbon removal credits on behalf of the US government. There are also concerns that the administration could dismantle an interagency effort dubbed the Carbon Negative Shot, which aims to scale up technologies and reduce the cost of carbon removal to below $100 per ton by 2032, which is considered economically viable number. An economically viable number. I missed the article. The government could have played an important part by advancing the research and development, as well as promoting the creation of common standards for an industry that currently operates like the Wild West, says Will Burns, co-director of the Institute for Carbon Removal Law and Policy at the American University in Washington, D.C. But those efforts are being swept away by the new administration, adds Burns. The DOE did not respond to a request to comment for Nature because government officials are very scared of saying anything about these kind of issues in public. Ocean alchemy, another approach. One project that seems to be moving forward for now is Loch Ness, which has received support through a $24 million public-private research program coordinated by the U.S. National Oceanic and Atmospheric Administration, NOAA. In August, assuming that the final permits come through, Subhas and his teams will release a solution containing 50 tons of sodium hydroxide, which is not used as an antacid for humans, alongside an inert tracer dye roughly 60 kilometers off the coast of Provincetown, Massachusetts. The researchers will then monitor the solution as it disperses, reducing the acidity of seawater and enabling it to absorb more CO2 from the atmosphere. I have discussed ocean pH elsewhere and how it's been regulated for millions of years at around 8.1, 8.2, and ocean acidification obviously means reducing the pH to become more acidic, and acidifying the ocean, reducing the acidity of the seawater enables it to absorb more CO2 from the atmosphere because of its ability to maintain its pH and alkalinity. In theory, Subhas says the biological effects will mostly be minor and positive, but monitoring during the experiment should help the team to assess potential impacts on shell-building organisms such as phytoplankton and diatoms. If you don't know, you can follow up on other podcasts. Studies using computer modeling suggest that during the week-long field experiment, the researchers should be able to measure how much CO2 is absorbed by the ocean as a result of their intervention. So it has to be additionality. Ocean is always doing something with the CO2. In some places it's taking it up, some places it's belching it out. So if you go to a place, then you must show that adding these chemical solutions actually increased the CO2 going into the ocean. If the team can show that it's possible to monitor and quantify how much extra CO2 is absorbed, the potential for scaling up is significant. With even a small increase in alkalinity, Subhas says, coastal countries around the world could collectively extract 1 billion tons of CO2 from the atmosphere each year, which is roughly equivalent to the annual carbon emissions from Japan and is about 3% of global emissions. Cost estimates vary widely for approaches that depend on altering the ocean chemistry to absorb carbon, but most suggest that they are likely to be cheaper than direct air capture. Of course, you have to always be sure that you are monitoring the impacts on the ocean ecosystem, etc. Loch Ness is just one of the 17 projects funded through the NOAA research program, and so far the efforts are all moving forwards. Other NOAA projects focus on a variety of methods to absorb CO2 in the oceans, including fertilizing the water with iron to grow more phytoplankton and farming seaweed. The program intentionally took a diverse approach, testing various options. We are not at a point yet where we can put together our knowledge and say which methods work at scale, says a former government employee familiar with the effort. They declined to be named because they were fired as a part of the mass layoffs by the Trump administration and they fear retaliation. Of course, the last component is the land, where you can green the land and put away some carbon, at least for some time. Similar efforts to remove carbon are moving forward on lab. Many scientists and entrepreneurs around the world are investigating ways to piggyback on the agricultural industry and help croplands to absorb and store more carbon. This includes projects that create a carbon-rich material known as biochar, made by converting plant matter into a charcoal-like substance that can enhance soils and keep carbon from returning to the atmosphere for long periods. There are details about biochar. You have to produce it with heating them, pyrolysis, which includes energy, high temperatures. So you have to make sure, in a life cycle sense, biochar is actually sequestering more carbon than the carbon released due to other processes in the production. Others are experimenting with the application of silicate-rich minerals such as basalt to agricultural fields. These minerals react with CO2 and water to form stable bicarbonate ions that dissolve and flow into the ocean, where they lock carbon away. Okay, I have a carbon cycle course where you can look up the chemistry details. A team of researchers led by chemist Matthew Gton at Stanford University in California is investigating a technique that involves cooking silicate minerals to make them more reactive and speed up the process of carbon uptake when they are spread across agricultural fields. Gton says the technique uses half of the energy of a direct air capture plant for a similar amount of carbon removal, while also boosting soil health, and the entire process unfolds over a single growing season. The team is planning a series of field trials in the United States this year. The biggest thing for us is getting buy-in from the farmers, Gton says, and only way to do that is to show them compelling data from the field, not from the lab. The strategies with the largest potential for carbon removal could come with agricultural waste, forest debris, and in some cases purpose-grown crops, which can be converted into long-lived products such as building materials. So you lock them up. Such techniques could provide the United States with upwards of 800 million tons of carbon removal per year, about 17% of the country's annual carbon emissions, at a cost of less than $100 per ton of CO2, according to a comprehensive study of carbon removal potential published in 2023. Why is it important? Because carbon capture will end up being a part of the portfolio of climate solutions. You will do all the renewables, EVs, efficiencies, other mitigation actions and so on, but you will still struggle to keep the warming from going out of hand, so you will begin to take out CO2 from the atmosphere, as we already are, but it's a matter of scaling it up, right? So this is at a plant in Squamish, Canada. The firm Carbon Engineering tests carbon capture. I read it all wrong. At a plant in Squamish, Canada, the firm Carbon Engineering tests carbon capture technology as opposed to Climeworks. This may be using a different technology, but I'm not going into the details. The challenge is in working out the logistics and bringing on board everybody from farmers and foresters to transporters and energy producers, says report co-author Sarah Baker, a chemist at the Lawrence Livermore National Laboratory in Livermore, California, which is now working on similar assessments in Denmark and Australia. It has to be brought down to the community level. Energy companies in Denmark and Sweden are taking a similar approach with a pair of bioenergy plants that are projected to begin operating in the next few years. These plants, which will burn a variety of materials ranging from straw to wood chips and other forest debris, are projected to capture more than 1.2 million tons annually. It will be a significant step forward, says Katie Koponen, I don't know how it's pronounced, and energy researchers at VTT Technological Research Center in Finland VTT Technological Research Center of Finland in Espoo. We have the technologies, but we have never used them at a significant scale. Koponen led a 4-year assessment of carbon removal options that ended last year with funding from the European Union's Horizon 2020 program. One lesson from that work is that European Union or Europe will need a portfolio of options in the next few decades if it is to meet its goal of achieving net zero emissions. One concern that is often raised about carbon removal is that it could give companies and countries an excuse to simply offset their fossil fuel emissions rather than transitioning to truly clean energy. To prevent this, Koponen and her colleagues also recommend that EU create separate targets for emissions reduction and carbon removal going forward. Another lesson from the EU carbon removal assessment is that it's not just about carbon. The most common and controversial approach in models analyzed by the Intergovernmental Panel on Climate Change, IPCC, is to grow crops to fuel bioenergy plants that can capture and sequester carbon underground while producing electricity. Although this can pull CO2 from the air, it also has negative impacts such as using substantial amounts of fresh water and fertilizers, as well as harming biodiversity and maybe competing with food security and so on. Scaling up bioenergy-based carbon removal to the levels contemplated by the IPCC will inevitably exacerbate those other problems, says Wolfgang Lucht, an energy system scientist at the Potsdam Institute for Climate Impact Research in Germany, who led the modeling work for the Horizon 2020 project. The bottom line is that there are no easy pathways to a future with massive levels of carbon removal, he says, and that means global leaders must hasten efforts to halt emissions now rather than assume that future generations will clean up the mess we created. We are really trying really hard not to burden the next generation with the enormous impacts of climate change, says Lucht. We should also not burden them with having to implement planetary scale carbon removal. Okay, there is another aspect to this. Even if we succeed at mitigation by taking out carbon, we still haven't paid enough attention to what the impacts will be on the climate, especially rainfall distribution, heat waves, extremes, and so on. So that aspect still has to be addressed. It's not like we are increasing carbon, extremes are getting worse, and we will take out carbon and extremes will go away. There will still be redistribution of rainfall, etc. So we have to see how that will work and who will pay a price for that. Okay, see you in the next topic.